And we're happy to have with us Julian Scheuer, who is currently in New York and soon joining us, talking about concavity of solutions to elliptic equations on a sphere.
Okay, thank you very much. Thanks, Jonathan, and thanks, Marco, for giving me the opportunity to speak in this nice online seminar. So I will talk about elliptic PDEs, non-degenerate and partially degenerate elliptic PDEs today in non-Euclidean spaces. And this is all joint work with Mat Langford, who's located at the University of Tennessee in Knoxville. And this is work from like the beginning of this year and partially ongoing. So we are motivated by hypersurface flows to look at this kind of problem. And the general setups here, we have a sequence MT of closed hypersurfaces in a general Riemannian ambient manifold, which we call N, and the dimension is N, which is usually assumed to be greater or equal than 3, in order to, so that we actually have a surface. And this family of hypersurfaces is moving by, according to this evolution equation. So X denotes the point in the ambient space. So you can think of X as the embedding of the hypersurface. And the normal velocity is given by a function of the curvature, which we denote by kappa I. So if you have an arbitrary surface of n-1 dimensions, we have n-1 principal curvatures associated to the surface at every point. And we take a function of these curvatures, and this gives us a normal velocity of the movement of these surfaces. And the most famous example, I would say, is the mean curvature flow, where you just take the sum of all these curvatures, or you can think of that as a trace of the Weingarten operator or the second fundamental form. They are all equivalent definitions. And we denote this function by h, like for historical reasons. This is always denoted by h, and the convention is that you don't average over this sum usually by using that notation. So we just take the pure trace. This is the most important example. Let me just give you a nonlinear example 2, which is given by the Gauss curvature, where you just take the determinant of the Weingarten operator or the product of the principal curvatures. And this function is usually denoted by k. Note that in arbitrary ambient manifolds, this does not coincide in general with the intrinsic Gauss curvature of the surface, like in Euclidean space. These notions are the same. But if you look, for example, if the ambient space is a sphere, then there will be a contribution from the ambient geometry coming to the intrinsic Gauss curvature that we know from classical surface theory. So this is really an extrinsic quantity in general. This is not only in the Euclidean space, it will be an intrinsic quantity. Okay, so that's a few examples, and let me give you like the most prototype result that are out there for such equations, curvature flow equations. So this is like the first paper on this topic in 1984. Well, in this setup, of course, there's previous work, but it's in this kind of result appeared in Huysken's 84 paper for the first time. So the result is as follows. So if n is greater or equal than 3, so you don't have curves, but you have surfaces moving, and f is the mean curvature, and we suppose that we have a strictly convex flow. So every hypersurface of the Euclidean space bounds a convex body. So that's equivalent to saying that the principal curvatures are positive. Then any such solution exists for a finite amount of time, which we denote by capital T. And in finite time, this flow converges to a point in the ambient space, and in the Hausdorff topology, if you like, and then you can blow it up by a rescaling factor to actually see something. So you zoom in into this point, and rescale by this time-dependent factor here and around this point, and you will see that this thing converges to a round sphere. So it becomes perfectly, totally umbilic in the limit. Right, and so you have a perfect information about the asymptotic profile of this flow. So I forgot to mention that please interrupt me whenever you have questions right away. So there's lots of room for discussion. I only have 20 slides. We should be well in time towards the end. So please don't hesitate to ask anything. I have a short animation in the curve case. I hope that everybody can see that. Is that visible? This media player here?
No.
I don't know a URL at the moment.
Maybe I have to share another.
You need to
screen.
share that window.
I'll share the. Okay. Now?
Yes.
Okay. Awesome. So we have a curve here, which is pretty irregular. So it is smooth, but it is definitely not convex. So it has all. So let me mention that this Huysken result I just stated holds for surfaces and higher dimensions. So the curve case is a little bit more general. So in the curve case, what this flow is doing, this mean curvature flow, you see in this animation. Starts moving soon, I hope. Yeah, there we go. It just balances out all kinds of irregularities. It will make the thing convex in finite time. And it will make the thing also, after more waiting time, it will shrink it to a point. And you can see that it becomes more and more round during this process. So if you would blow it up now to fix volume, let's say, then you would see it converges perfectly nicely to a sphere. So let's look at that. In particular, let's look at the behavior at the beginning, because you see several high curvature regions. For example, this tip here has huge curvature, and there are also small curvature regions in this, for example, these flat pieces. And you also have negative curvature regions like this here, for example. This is a negative curvature region. And you will just see that the flow shoots the high curvature regions inwards. It pushes the low curvature regions out so that everything balances nicely. So if we, for example, focus at these 2 points, like this one and this one, you can exactly see they sort of approach each other from the outside to the inside until everything is balanced, which is a very nice behavior. It's super surprising result. If you have a closed chord, for example, and you start, and I hold one end of this chord in the end, and I give one to John and Cardiff, and make an arbitrarily bad curve out of it, the flow will find a point between New York and Cardiff where this whole thing shrinks to, and it shrinks to that point in a very nice and smooth manner. So it's a super surprising result here. Okay, so this is like also in the 80s. That was not Huysken, that was Grayson and Gage. They did that like at the same time as Huysken did the higher dimensional case. So, okay, let me switch back to the other screen. So, right, so this is for, the animation was for one-dimensional curves. This result here by Huysken is higher dimensional surfaces, and you need a much stronger assumption here. You need a strict convexity in order to avoid singularities. And you will see a picture on the next slide on how to imagine why you need an assumption like this. But first, let me mention a few other results in the same direction. So I've introduced the Gauss curvature flow as well, and there are results due to Ben Andrews, who is in Canberra, Australia. So this result for surfaces in 3 space was like the end of the last century, and it was open until recently if that same result also holds higher dimensions. But Kong-Soo Choi and Toti Daskalopoulos, who is here at Columbia, they proved the same thing for higher dimensions. So they generalized the result for the Gauss curvature flow to higher dimensions. And also you can look at more general functions of the principal curvatures, and there are many contributions by many people. Basically, since this thing happened here in the 80s, they started to look at all kinds of curvature functions and proved similar results. Okay, so let's look at some techniques. How do you prove such things? And as you could imagine earlier, so from this animation, you saw that you need somehow control on the maximum and the minimum of the curvature during the flow. So it could be, so some principal curvatures could be negative initially, and some will be positive in the closed case, and they somehow you have to show that they approach each other, because a sphere has perfectly equal principal curvatures. So you need control on how the curvatures behave during the flow. And the first step is usually an oscillation estimate for the mean curvature, or for the curvature of the flow. And here's a picture of what can fail in higher dimensions. So look at this dumbbell kind of thing, where you have two large spheres at the sides, joined by a very thin neck. So this very thin neck has approximately two principal curvatures. One is almost zero, and one can be very large, this one which is making the neck to close up. And what happens during the flow is this high curvature region here, it is still high mean curvature, right? It's not the product of the curvature, it's just a sum. So it's very high curvature region, and this is a very low curvature region. So what this flow does here with this dumbbell is it will increase the high curvature even further here. And these spheres, they will not catch up during the flow. So these spheres want to shrink to a round point. So they will become smaller, but this process will take some time. And this process here, to make the curvature blow up, that does not take much time anymore. So what this dumbbell will do, it will split off. Unfortunately, I don't have an animation for that, but there are some. It will pinch off this thing. So you can actually prove that there's no way to avoid the singularity. And this is why Huisken needed this convexity assumption in his flow to get a smooth result in the end. There are a lot of generalizations now how to deal with these singularities today. And I mean, people have really analyzed these singularities until today. But for the smooth case, you need some assumption that avoids these kind of blow-ups of curvature. And yes, there's a question?
So that's if you take the mean curvature. What if you take the Gauss curvature or something?
Good point. If you do the Gauss curvature, the problem with the Gauss curvature here is that you will lose the ellipticity of the equation, or the parabolicity, because the symbol of the Gauss curvature is basically of the order of the Gauss curvature itself. So if you have a zero curvature, then the flow is not parabolic anymore. It's just weakly parabolic. If you calculate the linearization of the Gauss curvature flow, you will find out that the symbol degenerates at zero curvature regions.
Okay.
So this would not even be a well-defined, well-posed problem. If you start with something that has negative curvature, for example, the Gauss curvature flow is not parabolic.
Okay.
What you can do, there are generalizations when you have flat sides. That is due to Ben Andrews. When you have flat sides like this, the Gauss curvature flow is weakly parabolic, and you can get short time existence. And then you can show actually that these flat sides persists for a while. They stay flat. So this will not happen in a mean curvature flow. If you start with a weakly convex set, it will be strictly convex immediately by strong maximum principle. Because if you look back at the definitions of these functions, so what you need here usually is a monotonicity assumption on f to make this parabolic. So if you differentiate f with respect to a curvature, you will just get straight 1, no matter what the size of the curvature is. So that's a linear function of the principal curvatures. If you differentiate with respect to kappa I, you will just get 1. And so the mean curvature flow is always parabolic. But if you differentiate the Gauss curvature flow, the Gauss curvature with respect to, let's say, kappa 1, then you will end up with the product of the other kappas. And if one of those is 0, the derivative of f is still 0. That means that you have a weakly elliptic system here. And if you have negative curvatures, there's no way to make this parabolic. I mean, it will be the derivative will be negative at some pieces, and it is not well defined. It's not well posed. So that's basically the reason why these nonlinear equations usually require convexity all over the place.
Okay.
Can I just ask?
Yes, of course.
Have you are you going to talk about flows of this kind subject to constraints such as constant volume?
I'm not going to do this today, but this is part of my research too. So I'm really looking at these things too. So, well, in a sense, this rescale thing is flow like this, right? Because this rescaling fixes volume.
Okay.
And you can show that actually it also decreases surface area. So that will definitely solve the isoparametric problem in, of course, in the Euclidean space, there's nothing new here, but actually there are versions currently around in other ambient spaces where new isoparametric inequalities appeared from such kind of rescalings of curvature flows. So you can actually use it to prove geometric inequalities, which is like the second branch, a big branch of my research. Actually, I'm currently mostly I'm working at these things. And but what I'm talking about today is Harnack inequalities, and there these things don't apply. But I will come to that in a second. So what we want to look at, sorry, yeah. So what controls the oscillation? So we want somehow to show that the maximum mean curvature approaches the minimum mean curvature, to show that things become homogeneous in a sense. And the most natural thing that we all know of from parabolic equations, which controls the max by the min, is a Harnack inequality. And there are Harnack inequalities holding for curvature flows, and the first result in this direction, or one of the first results in this direction, is due to Richard Hamilton, who's actually famous for the Ricci flow, but he also did a lot of stuff in the mean curvature flow. He proved the following inequality, which holds along convex and compact mean curvature flow in Euclidean space. But what you see here is you get a partial derivative estimate, partial time derivative estimate on the mean curvature from below. Notice that this weird looking thing, I'll show you what it is. So Bij is just the inverse of the second fundamental form, which is well defined since we have a convex flow. And then you just apply that to the gradient of h. So this is a Bij nabla I h nabla jh is a positive term due to strict convexity. So in this inequality, this is actually a good term. You can put it on the other side and throw it away and get an inequality without that. So actually what you get from this is a differential, ordinary differential inequality, which holds at a fixed space point. So notice again, let me go back. This flow is, the variables of this flow are time and space, and the space variable I denote by psi. And this differential inequality is for fixed psi, just an ODE and T, which is very good because it gives you uniform control all over the space. So you have a really nice growth behavior of the mean curvature along the flow. And this doesn't really look very familiar in terms of the Harnack inequality, but what you can do here, if you have a, there's no slide on what I say now, so if you have questions afterwards, please ask. So if you have a point of maximum curvature in space-time and another point of minimum curvature in space-time, you can join them by a space-time curve and use this estimate along this curve to compare the maximum of the curvature by the minimum of the curvature. So you need some waiting time for that. As usual in parabolic equations, you will not get a Harnack at the same time slice. But if you wait for a little while, you can estimate the maximum by the minimum from this differential Harnack inequality. So this is very useful in curvature flows and has helped a lot in getting convergence results. So this is the first kind of these Harnack inequalities. So, and there are several extensions of this result. Basically, this all happened in the 90s. There was earlier work by Ben Chow for the Gauss curvature, which is a little bit easier because the Gauss curvature automatically preserves the convexity by definition, right? Because the Gauss curvature flow is not even parabolic if you lose convexity. So this was, from the technical point of view, a little bit easier. So it appeared a little bit earlier. Then at the same time as Hamilton's result, there's Ben Andrews who generalized that to a large class of F with some common assumptions. But this was also all in Euclidean space. So there's nothing in the other ambient spaces until recently. Well, like 4 to 5 years ago, we had some extensions to the unit sphere. This is myself together with my favorite collaborators, Paul Bryan and Muhammad Iwaki. So we did that for curvature flows within the unit sphere. So the ambient space is the unit sphere, and you have hypersurfaces in there flowing by such curvature flows with some assumptions. So you need the one homogeneity, that is a very common assumption. You need a strict monotonicity, as I said, to get the ellipticity of the flow, or the parabolicity of the flow. So that is like a necessary assumption. And then we need convexity of the curvature function itself. So you, for example, the mean curvature would be included, but also the trace, the norm of the second fundamental form would be included. So stuff like that would be included. Right, this is the first extension of this Harnack inequalities to the unit sphere. And then we have some more general ambient spaces as well, 2 years later, for the mean curvature flow in more general Riemannian spaces. So Einstein basically with non-negative sectional curvature. So extension means here basically the same inequality of this type holds for these kind of extensions, except where you have to replace h always by the flow speed. So this is, if you have a different flow, you have to use a different function here. So it's always the flow speed appearing. It's not always the mean curvature. It's always the f, the capital F that appears in this estimate. Okay, right, this is a little bit of background on this Harnack inequalities. And now I would like to say something about the proof and a new approach to this Harnack inequalities. This is a beautiful idea due to my collaborator Mat Langford and his earlier collaborator Theodora Bourni, and they showed nice relation of the level set flow to this Harnack inequalities. So for simplicity, we look at the mean curvature flow now and evolve a family of hypersurfaces by the mean curvature. Then we can define the arrival time. So we assume that the mean curvature is positive. Being positive means that the flow has one particular flow direction. It just shrinks the hypersurface. There's no going outside from the inside, like we saw in the curve shortening flow case in this animation, where everything can go all over the place, but we have a fixed flow direction. It just shrinks the hypersurface to the inside. Then you can make sense of the following function, which is called the arrival time function. It is defined on the ambient space. So omega is a subset of Rn, and you define W at a point X to give you the value, the time at which the flow arrives at this particular point. So in total, your hypersurface can be characterized by this set here. So you just take all points of X in the ambient space, at which the arrival time is exactly T. So this is you can definitely define the arrival time by this requirement to give you exactly T on the hypersurface. Right, and this is a function on the ambient space, basically on the area the flow exhausts in the time as long as it exists, right? And now we do a little computation. We want to relate the geometric quantities on the hypersurface, like curvature or tangent vectors, in terms of the arrival time function. And therefore we need a little bit notation. It's just 2 slides of computation, so I try to keep that brief. So let's just denote by G the metric on ambient space N, and the derivative, the connection, just by D, and G bar and D bar are the corresponding metric and connection on the hypersurface M. So now we can just differentiate this relation here, this characterizing relation, in space, for example. So let's do that in space. If you differentiate that with respect to psi, you use the chain rule and you get a 0 because T does not depend on the space, it's constant on the hypersurface. So you get dW applied to d bar x, just by taking the first derivative and using chain rule. Do the same thing again with respect to psi, and by the chain rule you get this relation. The Hessian of W applied to tangent vectors plus the gradient of W applied to the second derivative of x. Okay, this is a space derivative. Now we do time derivative. If we differentiate this with respect to t, we get a 1. And then we use a chain rule here. And we already use that partial t of x is minus h times nu. So this is mean curvature flow, right? This is exactly the characterization of mean curvature flow in terms of the arrival time function. So, okay, so these are 2 derivatives. And what we can extract from that information, if you look at the first information here, you can see that all tangent vectors are annihilated by the derivative of the arrival time function. That means that the gradient of W must be in normal direction. And that's what we can see here. And this factor h just comes from using 1. So you can show that the normal of the hypersurface in terms of the arrival time is given by minus the mean curvature times the gradient of the arrival time. So this is one first important relation between geometry of the hypersurface and ambient derivatives of the arrival time function. Okay, now we have to play that game again because we want to extract information on the Hessian of W. So we need further derivatives, and I will go to that briefly because you need some pen and paper to follow these calculations. So the second derivative, if you differentiate again with respect to time, you get the second derivative acting on the normal vector, which gives you this guy. You can easily see it from here. If you differentiate the lower equation with respect to time, you can see how all these ingredients pop up, right? You get a second derivative of W, you get a derivative of T, of H, and everything. So everything appears, so it makes sense. You would have to sit down to calculate that. We differentiate that also in space to get the mixed contributions on the Hessian of W, acting on tangent vectors and the normal. So you have a relation for that too. And then we get, if you differentiate the other, for the first equation with respect to space, you get information on the Hessian of W acting on tangent vectors. Right, so now you have all information in the ambient space on the Hessian because you can use the tangent vectors and the normal as an orthonormal frame in your ambient space. So basically we can calculate the Hessian of W, and we can just in summary write that into like a matrix. So the Hessian of W is given by 1 over h to the 3. And then this matrix denotes the appropriate entries. So the upper left part means that it acts on the normal vector twice so this is this entry here. The lower right part is the spatial direction, and the off diagonal is just the mixed contributions coming from here. So this is neatly written into a matrix, what this Hessian of W is doing. And if you happen to remember how the differential Harnack inequality looks, maybe I give you a short update on that again. So we have exactly these ingredients there somehow, right? We have the time derivative of the mean curvature. We have a space derivative of the mean curvature and the absolute term, and you will recognize these terms in the Hessian of the arrival time function. It's all there. So the observation now by Langford and Theodora Bourni was that this is related, so the differential Harnack is related to a certain concavity property of W. And the relation is that the function u equals root of 2 times W is concave. If that is concave, we can extract information from now. We will just suppose now that this is concave and calculate what comes out of it. So we can relate easily by the chain rule, like the first and second derivatives of u and w, and just evaluate what we had before. So we take u times Hessian of u by the chain rule equals Hessian of w minus the correction term, which comes from this product rule here. And now we can just include this correction term into our previous matrix, right? Note that this matrix D2W was given by this whole thing except this term here. But note that the derivative of W was annihilating all tangent vectors. So it only had contributions in normal direction. So it really only appears in the upper left part. So you just alter this matrix of W by the Hessian of W just by this part, and it looks like this, right? And now we have assumed that this guy is concave, so D2W is non-positive, sorry, non-negative. And we can make a Hessian test. We just plug a particular vector into this Hessian of U, and we know that in case of concavity, minus D2U applied to this vector must be non-negative because we assume that U is concave, right? And then we just put all the junk that we don't need anymore. We put this as a factor onto D2W, D2U, and then evaluate what's left. We get a sign here, and yeah, it really pops out. It's really nice. This is the differential Harnack inequality, really. Just looks a little bit different. This is invariant notation for this Bij thing that was written down earlier, but it's really the same. So also note that W at the hypersurface is exactly equal to T. So we have H over 2T, and let me go back one more time. It's exactly this thing. We have the time derivative of H plus H over 2T minus this mixed gradient guy is greater or equal than 0. And this is exactly what's written here. And it really pops out nicely of this very simple calculation, right? So we have seen that the differential Harnack inequality will follow from a concavity property of our arrival time function. And this calculation here holds in any ambient space. There is nothing special about it. But what Mat and Theodora did in their first paper on this topic is now to prove that along the mean curvature flow, the arrival time is concave. And so they got a new proof of Hamilton's differential Harnack inequality. So now, because Mat was aware that I have been working on these things in other ambient spaces, he came to me and said, can we do this? Can we get new results in other ambient spaces from this new method? And hence we got interested in the concavity of general elliptic PDEs on other ambient spaces, right? Note that the arrival time function really solves a degenerate PDE. So this is an elliptic equation on the ambient space. It's a little bit hidden, but because the second order derivative is hidden in H. So this is really an elliptic PDE, but it's weakly elliptic. It is not strongly elliptic due to the geometric invariance of the problem. You have a kernel in the symbol of this PDE. So this is really a degenerate elliptic equation on the ambient space. So the question is, when is W concave, or when is the root of W concave? So this got us interested in these kind of concavity questions. Oops, sorry. So what we wanted to do, to relax the restrictive assumptions I had with my other collaborators on the Harnack inequality by using this new method. But unfortunately, we did not succeed with this method. And you will see in a few slides why we had no chance to get this done. Still, I would not be talking about this today if we completely failed. So there's something we got out of this thing, and I will talk about this now. So in general, we wanted to get concavity properties of elliptic equations, and let me give you the method that is used here, also in the paper by Mat and Theodora in the Euclidean space, in the Euclidean case now. So this is a method which is pretty old, also coming from the 80s, and this is due to Korevaar, Kennington and Kawohl, on how to get concavity of solutions to elliptic equations. So let's look at the method. So let's suppose we have a convex domain in Rn, and you can write down concavity of a function just by requiring this function depending on 3 parameters t, x, and y to be non-negative all over the place, right? This is precisely a non-differential definition of concavity that is the common non-definition, right? And you know that we all know that if U is C2, we can relate that to the non-negative, non-positivity of the Hessian of the function. Okay, so the idea is we want to extract information on the derivatives of U at a minimum point. So if we want to prove that this function Z is non-negative, we can just assume by contradiction that it is negative somewhere. And then we want to differentiate the equation at this point. Assuming that's an interior point, we can differentiate it and get information about the derivatives of U by that procedure. So let's ignore boundary points at the moment and just do the computation in the Euclidean case, which is much simpler and where we actually get some results, or they got results. I was not involved in that Euclidean case project. So we suppose that we have a negative minimal point of this concavity function, and we ignore the boundary case at the moment. I will come to that 2 slides later. So let's just suppose we have minimal point, t, x, and y of this function. And we differentiate. So obviously t is not 0 and not 1, because in this case, z would be 0. So this is automatic, but we also assume that x and y are at the interior. And now we can just differentiate one time. So focus on the middle point. Here's a 0, which is the gradient in direction of z, in direction of x, and in direction of y. And now we just evaluate both of these. So if you do dxz, you get t from the chain rule. You get the gradient of u applied to the midpoint. So we denote the midpoint. So the convex combination point we denote by z, by little z. And on the from this term, coming from this term, we have t d of x just by linear, just a linear derivative. And on the right hand side, you do, on the left hand side, you do the same. And all of this junk stuff is 0, so we see that du of z must be equal to du of x and also equal to du of y, because t is non-zero, right? So this is nice. We have equal gradients at all 3 points. The left convex combination point, the right convex combination point, and the actual convex combination. The gradients are all the same everywhere. So now we can do the same again, because we have a second derivative to take, and we take a particular combination. We don't look at the full Hessian of z, we just look at this operator. We differentiate it in the j direction linearly. We interpolate linearly between all of these two variables and do the same in the I direction. But as we know that we have a minimal point at z, we know this is non-negative, right? And now we can just calculate from this equation what comes out. So we get a little bit more of a contribution here. We have a second derivative with respect to x, for example. So we get twice t. And then we get the Hessian at the point z, and so on, right? You can just follow, you can keep track of all the variables and see what comes out. And this is exactly what comes out. And if we focus at the midpoint now, so we have t squared Hessian at the midpoint plus 1 minus t squared Hessian at the midpoint plus 2t 1 minus t Hessian at the midpoint. This is like a perfect square. You can make this into a perfect square, and what comes out by simple algebra is this relation here. So the Hessian at the point z is greater or equal than the convex combination of the Hessian at the endpoints, which is pretty nice, because this is actually what we want on the level of the function itself, right? And now we have extracted that on the level of the Hessian of the function. Note that this is not a component-wise inequality. That is an inequality in terms of the Hessian. So this is, so u at the midpoint z is, so if you subtract, then the left-hand side is non-negative definite. So this is a inequality in sense of matrices. Okay, we have done nothing yet, right? We have just differentiated the convexity, the concavity function. We have not used any PDE, for example, right? But we have seen that at the minimal point, we get this nice relation of the Hessians. And now we use the PDE. So we have not used any information on the derivatives of u. So let's suppose we have a fully nonlinear equation of this type. So we have a function little f applied to a gradient and acting on the Hessian. And this is given by some function of space, the function u and d of u. So this is the framework, for example, for the mean curvature flow, which is why we were looking at this. So the question is, what structure conditions do we need on these data in order to transform this inequality to a similar inequality for the function itself? And now we can just keep track of everything, and we do that. We do that in the next slide. So here you see again. Recall we want to show precisely this relation at the midpoint, at the convex point z. So let's use the PDE. So we just write down the PDE at the midpoint. B of z and so on is equal to f at the midpoint. Okay, we have a relation on the function, on the Hessian of the function, right? So we can just use that we have monotonicity here. Let's assume f is a weakly elliptic, meaning that we have a monotonicity relation with respect to the secondary variable of f. And now we just include what we have calculated earlier right? So this is just the convex combination of the Hessians. Good, cool. Then we want to pull these things apart because we want to, in the end, we want to end up with b at the point x plus b at the point y. So we just split that apart. And this is, of course, only possible if the function f is convex in the second variable. So this is what we're using here. Okay, now we can already relate everything back because f of dux minus d2ux is equal to b at this point, right? So this is really using the PDE again. Also note here that we have replaced du of z with du of x because we know the gradients are equal. So that's good. There's no, we can just replace that easily. Okay, now we have that. And now we want to come back to a closed expression for b. And we can go back to pull everything into one argument if we have a concavity relation for b, concavity assumption. So suppose that b is concave in x and u, then we can do this estimate here. Right, so now we have a clean comparison between b of z and duz. These variables are the same. Only the middle variable is different. And yeah, we get that b of u at the midpoint is less or equal to b than the convex combination of the values of u. So if we now assume that b is strictly decreasing, this is only possible if we have the appropriate inequality between u of z and the convex combination here. So that's the idea, right? So you just extract, you set up your assumptions on the operator such that everything works in this calculation. Which is quite general. You can prove many things with these. I mean, a lot of things fall into these kind of equations. It's pretty general. Although it seems made up. Of course, it is made up, but it's still giving good results. So right. So these are the three structure assumptions we need on our PDE here. A weak ellipticity, which is nice. So we don't need anything like positive lower eigenvalue or something. It's just actually, it would apply if f doesn't even depend on the second variable. So it really gives you pretty strong information. So we wanted to transfer this calculation to the unit sphere. And in the next slide, I just give you the result, and then we see what we, sorry, I forgot the boundary condition. Let's first do the boundary condition. So what I haven't talked about yet is what happens if the midpoint or if this minimal point that we were looking at, so this negative minimum might have x or y being on the boundary of omega. What do we in this case? So of course, as always, you need just an assumption on the boundary. It's like this is more like a concavity maximum principle. So we just assume at the boundary that the function is already concave, meaning that the graph of u lies below its tangent planes at the boundary. So that's our boundary. It's like a Dirichlet condition, geometric Dirichlet condition, I would call it. We just require that, oh no, it's more like a Neumann condition actually, because it makes an assumption on the slope of the gradient there, of course, right? It's a Neumann condition, sorry about that. We just require the typical characterization of concavity in terms of the gradient to hold on the boundary. So right, we just pick a point x0 on the boundary, and if this relation holds with respect to the whole domain, if you arrange the second variable over the whole domain, then yeah, this is our assumption. And if we have that, we can show that if a minimum point would occur on the boundary, you can make a small variational perturbation into the interior to show that you could even decrease your function z. So it's not possible to achieve a minimum at the boundary if you have this geometric assumption on your function u. So this is what we have to assume. And then you get that the function u is concave. That's it.
Sorry,
yes.
Are the y's here meant to be y naughts? Or did I misunderstand?
This one? Yes, this is y naught. Sorry, this is a typo. Do you mean that one?
Yeah, and the one above, I guess.
Oh, exactly. Yeah. Sorry about that. That's a typo. That's a y naught. That's the minimum. This time I distinguished clearly between the minimal. Yeah. Either you put y here or you're right. This is a y naught and this is a y naught. Exactly. Okay, or geometrically, as I said, it's just the geometry behind this assumption is that if you put a tangent plane at the boundary, the whole graph of the function will be below this tangent plane. Right. Alternatively, so what Korevaar, Kennington, and others did in the 80s was they just formulated it as a concavity maximum principle. So the interior, there is no interior minimum. There's no interior negative minimum of this function, of this concavity function. That's what their formulation of the theorem was, more or less. And if you put a boundary condition, you get the whole concavity. Okay, so this is what was the Euclidean setup, and now we wanted to do this on the unit sphere, and here's the theorem. Looks nasty at first sight, but it's really just the same as in the Euclidean case. We discussed basically all of that. There are a few technical difficulties which cause some alterations to this. So this is just a list of the structure conditions I've given you earlier in the Euclidean setup. The major difference is that we have to put a modulus around the gradient. This will become clear in the proof. The setup is here. We have a geodesically convex domain in order to make sense of convex combinations. This means just that if you have a subset of the sphere, it's geodesically convex if the minimizing geodesics lie between 2 points, just lie into this domain. And you have a unique minimizing geodesic. There's a strong convexity, so you cannot have, there are no conjugate points in omega, and the minimizing geodesic is always in the domain. Right, so then we have a smooth function satisfying this elliptic equation. Structure conditions, again, are set up from the computation. Here's the boundary condition, which looks very similar. And then U is concave. That's the statement. And I will just give you, in the next few slides, I will give you an idea why we need some additional assumptions here. And let's look at these additional difficulties. So how would you set up the proof? Again, you would want to define a concavity function. Of course, now you have to make sense of the convex combination of 2 points, where you have to include a geodesic here now. So this is gamma xy is just a geodesic joining x and y. And now we have to evaluate the function u at this point. And it is also true that on the sphere, the concavity of a function is characterized by the non-negativity of this concavity function here. So this is what you have to differentiate in space, right? So first derivative.
I have a question, if I may. Is it important here that the metric is the standard metric, or?
This is very important. This will be very important. At this level is not important yet. So the concavity is true in any. You have a concave function. Well, it's the question how you define concavity on an arbitrary Riemannian manifold. So you can define it to be to get the non-negative of this function. And then you can show in any Riemannian background that this is equivalent to saying that the Hessian of U is non-negative. Mm-hmm. At this level, nothing is used about the ground metric, but later it will. We will need that a lot, definitely.
Thanks.
No problem. You're welcome. Right. So we want to say the same procedure. So here's the derivative. Of course, the x derivative is 0, but now you have to use a chain rule on this dude, and this gives you a derivative at the point z. And what is the derivative of the gamma with respect to x? Right? If you vary geodesics with respect to endpoints, you get Jacobi fields, and we denote this Jacobi field by j of x, which comes from the variation of this geodesic with respect to x. And here we have no problem, right? That's just linear again. So we just have this contribution here. The problem is now, what do we do with this relation? And the point is that the gradients do not coincide anymore, because Jacobi fields on the sphere are not linear. They are given by sines and cosines of the geodesic parameter. So we don't have equality of the gradients anymore, which is bad because we needed that in the calculation to relate all of these things with the PDE, right? So what we could show in the sphere, or let's say when we have non-negative curvature, is that we have an estimate on the gradients. And here come the absolute values. So we can show that in non-negative curvature, the gradient at the midpoint is less or equal than the gradient at the endpoints. And this is the reason why we have to include this kind of assumption here, that we can only look at the modulus, and we need actually a monotonicity property with respect to these gradient variables. This is precisely the reason. To carry through the computation in the end, we needed this kind of a structural assumptions. Okay, well, we could show this. This would also hold in non-positive Riemannian ambient spaces. This is not restricted to the sphere either, but we have to make a curvature assumption already at this stage. Okay, now the worst part begins, second derivatives. Right, we have to do that whole thing again. The first part is not a problem. We get a Hessian at the midpoint applied to two Jacobi fields. But now we also have to differentiate here with respect to x, right? J has to be differentiated with respect to x. And there the nightmare starts, because we get the second derivative of the geodesic, which we denote by k. And it's very hard to get information on these guys. So the only thing we have at hand is the Jacobi equation in general for J, which we can differentiate with respect to xi or xj. And then we get an equation for k. But this equation looks not nice, and this is where the sphere comes in, because in the sphere it's manageable, but in general Riemannian manifolds we have no idea how to deal with this guy. Because notice that when we did this earlier computation, you need signs everywhere. There's no way to estimate anything. You just need signs to make everything work. We need u to be the concavity function to be non-negative, so you really have to know what sign all of these terms carry. And if you differentiate that again, you will get all kinds of junk. So it will definitely not have a sign. And this we could actually prove, because even in the sphere you can show it's not zero and it will change sign. It will be a combination of cosines and sines, and well, we don't really know what to do with it. What we could do was this relation here. We could show this relation. We could show at the midpoint a particular combination of derivatives is zero. This is basically due to the symmetry of the Jacobi fields in the sphere with respect to the midpoint, because the Jacobi fields will attain a maximum or minimum at the midpoint of the geodesic. So we could get some information on this midpoint at this midpoint. And recall that in our earlier computation on the Hessian, we didn't look at the full Hessian. We looked at the particular combination of partials. And this is exactly the combination of partials on which we have some information actually, right? So this is how it comes in. And
sorry, what does the plus minus mean over there?
The plus minus means that you different. So this function z has two variables more or less in space, so x and y. So you just evaluate the Hessian at the vector which has an entry in the xi direction and an entry in the xi direction, and then you apply the x the same at this vector with respect to the other.
If you go back one slide, right. Yeah, here
here.
I'm talking about the plus minus that you have here.
Okay, yeah, you can pull everything back to a coordinate system. So these are vectors, right? So these are Jacobi fields are vector fields along a curve, and these xi's and xj's are all a local orthonormal frame. So these are parallel transported orthonormal frames. You pick an orthonormal frame at x, and you pick an orthonormal frame at y, and then you parallel transport them to each other, and it all matches up because we have geodesics. So it's a coordinate system parallel transported through the geodesic, and you can relate that into a common coordinate system on Rn, and there you add up vectors. That's how you do it. Yeah, there's a global coordinate system along the geodesic involved, in which you can do all these computations. This is a very good point, because these are actually evaluated at different points along the geodesic, right? But you can relate everything to the concavity point as a reference point, if you like, and then add up everything in the tangent space of that point. That's technically that's a technical issue that you have to deal with, but that's possible to relate all this within one coordinate system. Is that answering the question?
I think maybe we can talk about it later.
Yeah, we can do it later. Right. So with this combination, we get information on this thing at the midpoint, and if you do look at the general concavity function, you have no information on the location of t, right? T could be anything between 0 and 1. But the nice part is that is a beautiful result due to Jensen from the beginning of the 20th century. If you have a continuous function, concavity is equivalent to midpoint concavity. There's a neat induction proof you can do. So you can, function is also concave provided this relation holds. Yep, that's it for all points x and y. So what you just do, you set up your concavity function as a 2-point function, forgetting the t parameter, and just use the 1/2 as a parameter, make a 2-point function out of it, and then you are automatically at the midpoint, and then you can really throw away this term here in the calculation because it's 0. If you look at the right combination of case, this will just disappear in the computation, and you still get your information on the Hessian that you want, right? In the end, what you wanted to do is, sorry, go back farther. We want this in the end at the minimum point, right? This is our goal, and in order to get that, you need to really get rid of this junk term. And the idea is here to just use the midpoint as a definition, and then use this crucial lemma here to show that everything vanishes. So this is how you deal with this term. And then everything goes through. Right, you have actually seen how the proof proceeds. You just set up the PDE and extract the structural conditions you need to order to get a result, and that's how we did it. And actually, this is all I wanted to say. And since I will join the Cardiff department and you guys, and I'm very excited to see you all in person at some point, and I have to practice a lot. And I say the Korevaar for your attention. Thank you.
Thank you very much. Are there any questions?
I will ask a question if I may.
Yeah.
So from the proof, it seems to me that it's crucial that A, you are in a geodesically convex neighborhood of a certain point, and B, that you actually use the standard, the metric on the two sphere because of this midpoint property, right?
Yes, basically because you have to differentiate this Jacobi equation, and on the sphere, this Riemann tensor has a very nice structure in constant curvature spaces.
Mm-hmm. Yes.
So if you don't assume that you will get gradients of the Riemann tensor, and there are no reasonable geometric assumptions that make you deal with that.
Mm-hmm. But is there any hope of extending this result in other types of spaces? Say, you still need geodesically convexity in order to define what convex means,
yes,
because you will need a geodesic somehow. But is there any idea or any hope of generalizing this to spaces where you don't have the standard metric?
Yes, well, we have, of course, tried to carry through the computation as far as we could, but and I cannot confirm that it's not possible. But and we could do some things we could do in more general spaces. For example, as I said, this gradient estimate. Where is it? Right here. This would hold in non-negative curved spaces. Mm-hmm. I think so. So far you will get it, and then you will have to see what. Yeah, we didn't really look at this lemma. It might hold. It's not excluded. So it's definitely worth to look at this. So the answer is maybe. Work hard and try, and maybe. Yeah. But what I probably can exclude is the hyperbolic space. If you're after that, for example. I think the result is wrong in the hyperbolic space, because the reason for that is why I think that, maybe this result, the fundamental gap conjecture. It says in the Euclidean space, the fundamental gap conjecture for the Laplacian says that the difference between the first and second eigenvalue of the Laplace operator has a certain gap, which is a fixed value, which is greater or equal than a fixed value, which corresponds to a model situation. And this fundamental gap conjecture is also valid on the sphere, but it's not valid in the hyperbolic space, as was recent. There were recent counterexamples to the fundamental gap conjecture in the hyperbolic space. And I think that this is highly related because the proof of the fundamental gap conjecture uses a refined concavity property of the solution of the, of the eigenfunctions of the Laplace operator. And in the sphere, it was possible to show this concavity, but in the hyperbolic space, as this counterexample shows, it's not possible to show this concavity. So I suspect that there is big relation between equations of this type and concavity properties of them to the fundamental gap conjecture, which fails in the hyperbolic space. So I think in the hyperbolic space, there might be no way, depending on what you're after. So, but I think you can extend this result maybe, but not to all kinds of situations.
Okay, thanks.
Welcome.
Any other questions? So maybe I'll ask something. So the equations are always local. They always depend on one point. What about non-local variants of these things? Sort of some kind of dependence on some global features.
Yes, I have not seen any. Well, I've seen some special cases, but I'm not an expert on this. I must admit I don't really know what's done in this direction. So from the proof, I mean, as I said, so this first calculation does not depend on anything. So this part of the proof definitely is valid. You can see what you get from this. I mean, it's a local information you get, so I'm skeptical that you will get global information from purely the PDE, because there's also an interesting interplay between locality and non-locality. Note that we need a global assumption on the domain. So the Harnack inequality I was talking about initially is a local inequality, and you can prove it locally. So the proof by Hamilton was local, just by maximum principle applying to some test functions. This approach needs the information that the domain you're working in is actually already convex. So you definitely already need that the flow shrinks to a point, right? Because otherwise the flow will not extract a convex domain in the ambient space. Fortunately for the mean curvature flow, this is not a problem to show that the flow at least converges to a point. The hard part in mean curvature flow is always to get the limiting shape. But I already see here that there's an interplay between local and global assumptions. And I think from the purely local PDE, from this approach, you will not extract much information about global quantities. If you put like an integral into the equation of some entropy or whatever, then I don't think from the pure PDE will extract much information. But this is really a vague speculation. I don't really know.
Thanks. Any other questions? Okay, if not, then let's thank Julian again.
Thank you very much.
Yeah.